So here's that first example that we could not do using our old methods, arctan, U substitution. We didn't consider integration by parts, even though that was on the table. I am going to recognize U substitution fails. I do see that denominator expression does factor. So I'm going to use that. I'm going to say, let's come in here and let's see how that breaks down. Okay, so you've already ruled out some of your other techniques, and now we're going to decide to do this partial fraction decomposition. Well, what does this mean? I would really like to break this up into smaller pieces. So I am going to come in here and sort of take this expression and say, okay, I'm going to work on this. What I'm going to do is just kind of off to the side deal with this statement. What I have here is I have 1 over x plus 3 x minus 1. Those are distinct linear factors. So using that kind of flow chart above, I'm going to set it up as a over x plus 3 plus b over x minus 1. You're not going to be left in the dark and just making up coefficients a and b that somehow work out. But you are going to decompose this, and you're going to make sure that this works. So here's how this works. It's very algebraic. What I'm going to do is come in here and say, all right, let's fly back to Algebra 1 and Algebra 2. What I have here is a rational equation. And the easiest way to handle a rational equation is multiplying everybody through by the LCD. Meaning if I were going to get a common denominator, what would it be? What would be both of those factors, the x plus 3 and the x minus 1? You multiply every single term by that. You maintain the equal sign, right? You don't mess that up. So when I do that, notice what happens here on the left-hand side. You know, the factor of x plus 3 goes away, and the factor of x minus 1 goes away, and all you have left is a 1. Over here on the right, the first fraction, the x plus 3, can cancel with what's in the denominator, but you're left with the x minus 1. That's still hanging out. And over here in that last one, the opposite happens. The x minus 1 cancels out with what's in the denominator. You're left with the b, and then that extra factor of x plus 3. Okay, so this is another way to imagine that statement that I had up above in pink. Now, again, you are not going to be fishing and dreaming up A and B values to make this work at all. What you're going to do is you are going to dream up something. You're going to say, wow, if I could only let X be something super convenient so that one of these binomials would fall apart to 0, I'd like to do that. So let's do that. What that means, I'm going to say, man, what if X were 1? And if X were 1, that would be pretty amazing because I'm going to plug it into this statement, but anywhere I see an X, I'm going to replace a 1. So what does that give me? Well, 1 minus 1 is 0, and 0 times A is a big fat 0. That's the whole point. And what I have here is I have 4B, right? B is multiplying 4, so let's just write it in a better way, and I can eyeball this. I mean, if I'm solving for B, all I have to do is divide by 4, right? B equals 1/4. That's pretty good. Okay, so you did in fact, dream up this idea of like, hey, what am I doing here? You're dreaming that part up, but you're doing so very efficiently. You're looking at these binomials to see what to do. So the next one I'm going to dream up, I'm going to look here. What would I let X equal to let that whole thing go to 0? Well, let's think about it. That would be a -3. You're going to decide that based on what you see. So again, run through this whole thing in orange here and just keep plugging away. Anytime you see an X, replace it with a -3. And then I'm going to evaluate. So that would be -4 times A. Over here, -3 plus 3, that gives you that big fat 0. And again, really quickly, you can pretty much see in your head here that A equals -1/4. So you algebraically solved for what the missing link was here. What are these coefficients A and B in this decomposition? And that means I now know those missing links. So what that allows me to do is come back over here to the left because you've done all of this, algebraic legwork. And I can continue on with my equal sign. I know that colossal one giant rational expression breaks down and decomposes into these two separate fractions. A over x plus 3 plus b over x minus 1. That is a legal sort of next step. Now, of course, I need to see all of this work. This work is incredibly meaningful and important to me. I grade a lot on partial credit, so I can't not see this. If this is not on your paper, you're not getting credit for this. I just want to be really, really clear. I need to see this work. And it needs to be sequential. Okay, so what do I have here? I have two separate integrals then that I can work on, because let's be honest, as long as they're separated by plus and a minus sign, I can handle these separately, which means I can take the negative 1/4 out of that first integral and just handle this. Just do it piece by piece. I can do the same thing on the next one. Take out the 1/4 and just worry about the integral of 1 over x dx. These individual pieces are much better. Now, normally I avoid trying to do things twice, but look, doing these two smaller integrals is so much easier than handling that colossal mess you had at the beginning. I can, dare I say it, I can almost do this in my head, although, well, I can, but some of you may want to write it down. You are doing a u substitution. It's just that u is different in each of these cases, but it's a straight layup here. du equals dx. So you end up, integrating 1 over u du in both of those cases. This is what you're left with. It's just that, well, the u is different, and of course, these extra coefficients slide down. So what's my antiderivative here? My antiderivative is negative 1/4 natural log absolute value of x plus 3, and then plus 1/4 natural log absolute value of x minus 1. I think this answer looks lovely. I think I'm also going to take the time to show you a different representation of that same awesome answer, because it's going to be worth our time. What I want you to imagine doing is I want you to imagine sort of let's just move these things, put the positive expression in front of the negative one, and I'm going to factor out a 1/4. So 1/4 natural log absolute value of x minus 1. Then I have a minus in front of the natural log of the x plus 3. And I want to remind you again about those log properties. You see that minus sign in there? That means they can congeal together as one logarithmic statement. You will see this from time to time, and I want to show it to you. You should be simplifying these. Okay, so it's worth your time to do that. All right. Now, we are also going to go over example 6 right now. Okay, now, sorry that this document got a little bit off on Microsoft Word before I saved it. On yours, I'll make sure that I correct it so it's not awkward. But we are going to do example 6, which is this guy here, this 9 over x squared minus 4. Very similar situation. This is problem number 6 from the first page that, again, we did not have the skills to handle because there's no plus sign here. It's not an arctan. It's something different. Lucky for us, you're gonna come here and say, okay, I know u substitution fails. I know it's not arctan, but wait, hold on. I can factor that denominator. That's going to be your tip-off to, all right, I'm going to skip over integration by parts, and I'm going to go with partial fraction decomposition. So again, you're going to come in here and you're going to say, all right, I'm going to reimagine this right here. This is what you're going to work on and say, let me take some time and rewrite that algebraically. I'm just going to kind of move over to the side, and I'm going to say, well, if I have this expression, this rational expression, and I want to decompose it into smaller pieces. These are, again, distinct linear factors. They are different. So there's my setup. I am going to solve this algebraically, like you did in Algebra 1 and Advanced Algebra. You are going to handle this rational equation, which means you're going to come in here and you're going to multiply every single fraction by the same expression, by your LCD, if I use that old lingo. What you would have as a common denominator if you were going to get one. And so you can kind of see over here on the left, everything cancels. All I have is the 9. That's great. Over here, the x minus 2's cancel. I have the a, and then that extra factor of x plus 2 hanging around. I have the plus sign. I'm going to have b. The x plus 2 factor cancels out, but I have that extra factor of x minus 2 hanging around. So I've just reimagined that statement in pink to this statement in orange. Now again, you are not going to be guessing the values of A and B because we'd all go insane. What you're going to be is be very specific and very crafty about the X value you choose to use. You're going to solve for A and B very efficiently. You're going to look at these guys and say, you know what? I've got a good idea. What if I let X equal 2? If I let x equal 2, I'm kind of making a beeline for that binomial. I want that to be 0, straight up. So what I'm going to do is go through this whole equation in orange, and anywhere I see an x, I'm going to replace a 2. And the whole point of doing that, I know that I get like 4a over here, but I get b times 0. Well, that is 0. So just eyeballing this really quickly, again, you're just going to divide by 4. What this tells you is that A is positive 9/4. You are also going to take a look at it and say, what else can I do? Like, what else can I do to kind of imagine an X? And you're going to look at this guy here and say, well, what if X were negative 2? That's going to make your first guy go to 0. So give yourself some space, right? Anytime you see an X, you're going to replace it with a negative 2. And the whole point here was that this whole term collapses to a 0. A times 0 is 0. What I have here, though, is I have negative 4 times b. So what that tells me, really quickly, just divide through that negative 4. B is negative 9/4. And that is really great because now I have this partial fraction decomposition instead of looking at this, you know, huge integral over here that I have no skills to integrate. I can just kind of keep coming at this with an equal sign. You've just algebraically proved, hey, this giant fraction is the same exact thing as these little sort of components that are much smaller. And this is manageable. So I'd much rather deal with two smaller pieces than this colossal whole that was really overwhelming and impossible to do. Now again, because they are separated by a plus or a minus sign, you're allowed to handle these separately. So let's go ahead and do that. Let's take that awkward 9/4. It's really just a coefficient. Let's take that out. And let's take, actually, you know what? Let's take out that negative 9/4. I'll just put in minus, right? And the integral is 1 over x plus 2 dx. So you can handle these all separately. And again, technically at this stage of the game, you are doing, like two little mini u substitutions. You're letting u equal x minus 2 in the first one. You're letting u equal x plus 2 in the second one. And I would think it would be appropriate if you just kind of do this part in your head. That's fine. It's going to be 9/4 natural log of u, which is, well, the absolute value of x minus 2, minus 9/4 natural log of the absolute value of x plus 2. That is an answer, although I should be simplifying this. So this is a good answer. Your antiderivative is over. However, keep in mind what you can do. See, these coefficients are exactly the same. Let's do what we did in that last example. Let's factor out that 9/4. And let's constantly remind ourselves about those log properties that keep coming back to haunt us. And make sure that your handwriting is clear. It really has been. You guys have been pretty good with that. That those absolute values, make sure that they don't slide and get lazy and look curvy. Because if they look curvy, I'm going to mark you wrong, which is why I tend to bold them out. Like, no, I really mean for this to be absolute value. Okay, so those are the most used, example problems for partial fraction decomposition. And I'll show you some other more advanced ones as well in the next couple of videos.